Right, so here I'm going to go through 1.2 software and software development. And these are the sections I'll be covering in this video here. I'll probably do at least 2 videos on this section because it's quite a long section. So first of all, what is the function and purpose of an operating system? Well, the whole point behind it is to provide a layer of abstraction for the user. They don't need to know exactly how the hardware works to use it. So the users can interact with the software that's installed. The software will interact with the operating system, although sometimes the user can directly. And the operating system will interact with the hardware. Okay, so the main thing is to provide an interface for the user. Okay, it also manages hardware and it manages the software and does a lot of other things we're going to cover briefly. So there are 2 types of user interface we're going to look at. One is the command line and one is a graphical user. But basically, a user interface allows the user to control the computer. It hides away the complex parts and keeps it simple, or tries to. Okay, I'm not going to dawdle on it because it's quite an easy topic. So these are the 2 types of command line. You've got one like DOS or Linux has a command line. And obviously Windows, iOS, Android all have a graphical user interface. So don't just think by default that GUI is the way to go. Obviously for the mainstream desktop computer, this is the most useful thing. But if you're being a web server for Google, do you really need a GUI? It might be they set it up with a GUI and then drop out into command line to run the web server, because the advantages of a command line interface are that it uses less resources. And by resources, I mean memory, processor usage, and of course power, which is very important to a company because power is money. If they have to use a lot of electricity, it's going to cost them more money. If they have to have a more powerful computer, it's going to need more CPU and so on and so forth. Okay, so you can make scripts in a CLI. So what I mean by that is you could make a small text file that does like 5 different things in a row. That can be quite handy. If you've got to do that on a graphical user interface, that's quite annoying. Okay. It's easier to follow a set of instructions in a command line. If you want to install some software in Linux and you've got to do all this complicated stuff, it is really kind of a copy and paste job. Whereas obviously in a graphical user interface, if it says click here, go to settings, go here, click this, obviously it's not impossible, but it can take longer and be a bit more difficult for the layman to follow. So obviously this only needs a keyboard as well. It doesn't need a pointer device, another small bonus. But of course, a CLI is harder to use. You've got lots of commands to remember. And if a user writes wrong commands, then they could be easily making a bigger mistake than you might think. They could be deleting all of something or moving a file somewhere. It's a lot easier to make a big mistake in command line. So obviously it's the opposite things for a graphical user interface. They're a lot easier for beginners, but they do require more resources when used. They have a lot of shortcut keys. That's quite useful. You can have shortcuts to do things. But it does take longer to create some software because obviously for the programmer, they have to now make a GUI. So it can be a little bit annoying. But of course, one of the main things, it's easier to run multiple programs at once. It's quite difficult or nigh impossible to run multiple programs at once with a command line, at least not well, and at least not interface with them. They could possibly run in the background, but to actually interface back and forth and switch back and forth is quite annoying. Obviously, it needs a pointer device on a graphical user interface. And an advantage is that it's much more aesthetically pleasing. It looks better, okay? And I don't know why I put that in a disadvantage because it should be an advantage, so I'm going to move it there. And it can also have things like built-in spell checkers that check all the programs rather than just the ones that you install. So any program could make use of a spell checker or a dictionary in a graphical user interface, for example. Like, for example, I'll give you an example. The inbuilt disability function of reading out the text to help with visually impaired people. You don't have to write that for your program. That's built into the operating system. So your program can use that. Other things that the operating system controls is peripheral management. So it manages the way in which hardware interacts with the software. A peripheral is any piece of hardware that isn't connected to the CPU, a keyboard, a mouse, a printer, a hard disk drive. And the operating system manages all of those. And it allows them to be updated, and you can do various things to them and you haven't got to worry about it. So file management is quite a useful part of the operating system. It talks about how files get saved, where they get saved, who has access to files, how they can read files or write files. And basically, this is a form of abstraction, which I talked about before, in that a programmer doesn't need to know how or where a file is specifically saved on the hard disk drive. It just needs to do a save and give the path, and the operating system will sort that out for you. So it's a level of abstraction for the programmer. That's what it means. That's what the whole point of an operating system is. So that's the main things it does. There are many more which we've covered in the GCSE, and you can welcome to watch the rest of that video if you want some more. But they are quite obvious. They are quite simple. I'm not going to dwell on them in the A level because you probably have seen them. But I will leave a link to the GCSE video. So one of the important ones that's listed in the A level is the memory management part of the operating system. So the operating system allocates memory between the programs that are open at the same time. The programmer and user do not need to know where in-memory data is being held. It is the purpose of the operating system to do this. Another level of abstraction. The programmer makes a variable called name. It doesn't need to know whereabouts in memory name is, that or how it's made. That is part of the operating system. Now we'll look at two methods for allocating memory. The one that everyone uses and the other one. So basically paging is the main one. That's what's covered mostly in this entire section. So the operating system divides the memory up into pages which have identical equal sizes. Okay, so in this case, my main memory is divided up into 1 meg chunks. Okay, the operating system then gives an address to each of these pages. So rather than giving an address to each individual part of memory, we've chunked it up into 1 megabyte blocks, and we're giving an address to each megabyte. Just to be clear, the size they choose is up to the operating system. 1 megabyte is really a generically random number I picked. When a new process is created, and by process, remember, every program has one process, the main one. But if you're having a program that can use multiple cores or do multiple things, you can start new processes. But just think about every program has at least one process, but some programs can have more. So when a new process or program is created, the operating system will allocate the appropriate number of pages to it, although those pages may not be physically next to each other in memory. This is called non-contiguous. So contiguous memory, or anything contiguous in life, is next to each other in a sequence. Non-contiguous means not next to each other. So in RAM, all the pages could be all over the slot. And the reason this might be the case is very similar, if you remember before, if you've heard about it, to defragmentation. So for example, it would be common sense for the computer to allocate the 4 meg in a row. But what happens is, after a while when RAM fills up, what happens if we were to delete, let's say we had some more data down here. What happens if we were to finish with program B? Well, now we have 3 megabytes in the middle of other data, and you can't just unuse that until you've got a big, enough space. So basically, as processes finish and pages get removed, it leaves gaps in memory, and so the computer just fills those gaps as it goes along. It's no trouble for the computer to do it non-contiguous, as that is not how memory works. It doesn't really care if the data is next to each other, because at the end of the day, that's not how memory works. If it was a hard disk drive, for example, it would matter because of the physicality of a disk drive. But as it's electronic memory, it doesn't really care whether it's next to each other or miles apart in terms of the addresses. So what happens is, the operating system has a paging table here, which lists where the actual logical address is to the physical address in memory. So I've made up these page numbers. They're addresses to the pages. So A0, A1, A2 and A3, the operating system has given 4 pages to. A3 hasn't used all of its page, but it has to be allocated the whole one. So you can see how paging can be slightly more inefficient because it does leave gaps if an unused page is not full up, if a page isn't full up. So anyway, so as these are not next to each other, as you can see here, 1, 2 and 3, AO, AO1 and AO2 are stored at 1, 2 and 3 respectively. And actually AO3 is stored in page 9. Okay, so you can see that it just has a table that says where are the pages. Okay, and the same thing here. Okay, so these are stored at these numbers and these are stored at these. Nothing too ridiculous there. So that's paging. The other alternative is segmentation, and that's where basically you can do the same sort of thing, but they can be divided up into blocks of different sizes. However, it is the compiler, so the person who writes the program and therefore the compiles the program, rather than the operating system that can allocate the segments. So it's rather than the operating system taking charge of how much space is needed, you would have to do it as a programmer. Now, it's more efficient because you're not going to have these gaps, but it isn't as fast. Okay, paging is much quicker, maybe because it's been more optimized. And so generally, because you know that everything's in set chunks, so you can skip to certain sections quicker. But yeah, so that's basically the reason. Paging is faster, but less efficient in terms of memory usage. But memory is getting less costly, and speed is always important. So that's why a paging system is generally the most used. So virtual memory, we've done this before, but virtual memory happens when the computer suspects or thinks that it's about to run out of main memory, and by computer I mean operating system. Windows, for example, will begin to use virtual memory. So it will move applications or data. What it will actually move is pages. It doesn't even need to move all of the program. It could just move a few pages out. It will move pages out, and now you're going to see the link to the word, onto the secondary storage into a page or paging file. That's why it's called a paging file. So the pages from here, so here, I know this is a very small amount of RAM, but let's say we need to free up 2 megabytes. It might just move C3 and C2 out. Now you might think, why doesn't it move all of it out? Well, the problem is it takes time to move all of it out. It's not free. It's only 4 meg, but let's presume it's 4 gig. It would take time to move all of it out. And then when you go back to program C, you've got to move it all back. So, it is annoying. So you don't want to over waste movement. So what it does, it moves some of these pages out of RAM onto the hard disk or solid state drive, and then it can delete them out of RAM and then free up the space for the applications that you need. If you go back to that program, it will have to do the opposite. It will have to shift something else out of RAM into the paging file and then shift it back. So this is what you can see, that virtual memory is a stopgap. It doesn't solve the problem of low RAM, because you think about it, you've got to load a file from your solid state drive into RAM. At the same time, you're thinking, oh no, we haven't got enough space. We better move some stuff out of RAM onto our solid state drive. And I think you can see here how you're moving back and forth the data. This is going to slow down your machine substantially. In the older days, when hard disk drives were more important, I mean, this is still true now, but obviously it's phasing out. Because the hard disk drive has an actual head that moves around, and you're loading and saving in sort of quick succession, it means that you're loading and saving from different areas of the disk, obviously. And the head of the disk would move back and forth really fast. It tries to get data and save data in different places. It would make a loud noise, and this would be called disk thrashing. Really, this could used to be able to cause damage, but more realistically now is it will just slow down the machine. This is, of course, only important to hard disk drives, because solid state drives don't care about where you're getting data from and to. So it will not have this issue of the head having to physically move back and forth. It's still going to have the problem of having to save and load off of it. So it's not a great solution, but a solid state driver's virtual memory is significantly better because of that fact. So now we're going to move on to interrupts, which is part 3 of this section. So when you're running a program, it is possible and likely that something more important might need to suddenly take over the CPU. And interrupts allow us to do this. So we're going to look at what can cause an interrupt. Well, software that's running on your computer can interrupt any current running program. Any hardware device, so like if a printer got jammed, it could send an interrupt back to let you know that there's a problem. And the CPU clock can cause an interrupt if it wants. So let's look. I've given an example here as well of why I bother with interrupts. A program is being executed when the virus software detects a virus on it. This must be stopped and dealt with prior to execution, so an interrupt request might be called. So if a virus was found on the computer, an extremely high, the highest priority interrupt would be sent to the CPU, and execution of the current program would cease and the virus protection would take over. This seems logical. I'll show you an example with the FDE cycle. So you're normally fetch, decoding, executing and going back to the start. But actually what we do is we fetch, decode, execute, and then we check for an interrupt. If the answer is yes, we back up everything that's in the current registers, all the program counter, all the stuff, all the accumulator gets backed up. And then we handle the interrupt request. And then when it's finished, obviously they would get, we carry on handling interrupt requests. And then when it's finished, the register would get copied back. Okay. Now I'm going to talk to you very quickly about how this happens. Right, so how does it do all that copying stuff if there's an interrupt? What does it do? So basically, first of all, we've got to introduce you to a concept in computing called a stack. And this is just to break away from interrupts for a minute, because interrupts use stacks, but they're used in a lot of areas of computer programming. The idea behind a stack is to think of a stack of bricks that a child stacks up. When a stack is empty, there are no bricks there. Then say you place a red brick on, and then a green brick on, and then a blue brick on. Now, that would be called push. So you would have pushed the red, pushed the green, pushed the blue. Okay, and then after that, you have the word pop, and pop will remove the most recent one from the stack. So as you put red, green, and blue, if you pop them, they would go blue, green, and red. I will show you, they have what's called a last in, first out policy. I'll show you my terrible program I've written here, where I've made a stack. So I'm going to do one for push. So I'm going to add to the stack. It's empty at the moment. I'm going to add a stack 88. Okay, so if I print the stack out with 3, the contents of the stack is 88. 88's at the bottom of no stack, so it's the only element. Let's push another one on, and I'm going to push 20 on top of it. Now, when I print that, you see 20 is now on top of 88. I can do the same again. I'll do 43, print it, and now you can see that I'm adding to the stack on top. Now, the only way I can get things out of the stack is to pop them, and that will return them. It will return them and remove them from the stack. If I type pop now, I'm going to get 43. 43 there. Not the best, most pretty program I've written, but there we go. We'll deal with it. It does the job. The point is, if I now print the stack, I will have, of course, 20 and 88 left. Okay, so it's a very basic. And of course, if I pop the stack again, I'll get 20, then I'll get 88, and probably it'll crash at this point because I'll try to remove an element that's blank because I did not put any error checking in. Good coding. But the point is, it was just a very quick example of what a stack is. Now, they can be used in many things. Some games, Magic the Gathering uses a stack method where you cast spells and they sort of go on a stack and then they're done in reverse order. So the last spell that was cast is actually cast first. But that happens in many areas. Lots of areas of computing use a stack, and so do interrupts. So now you know what an interrupt request stack is, sorry. Now we're going to see how an interrupt request uses a stack. So what happens is, when there's an interrupt, the processor halts execution and moves the contents of the registers onto the stack. So basically, you would end up with a stack with all of the program counter and the other registers that you need in that stack, in one sort of chunk. It's not obviously going to set it up separately. So then what would happen? Okay, so you've got them all in the stack. So the interrupt service routine would do the interrupt, would handle the interrupt. Okay. But here's the weird thing. Interrupts themselves can also be interrupted if they're interrupted by one of a higher property. And then what would happen is, then that interrupt, because it's basically now a program that's been interrupted, would also be put on to the stack. So I'm going to show you with my top quality graphics that I always produce, not in Paint at least. So, right, here we go. This is the stack. So we are executing process A. So process A is executing, code, execute. Let's just say it's just started. Hasn't even executed the first bit. Bam! We get an interrupt request with medium priority. So, okay. So what would happen is process A would get placed onto the stack. Okay? And we'd now be executing process, the interrupt request. Okay? Now, interrupt higher one. Antivirus maybe's come along and said, excuse me, I need to interrupt you. More important person coming through. So then what the computer would do, or the operating system, and would move this onto the stack. And then this would get executed. And if there's a highest one, if even a higher one was to come along, this would get placed on top. Let's say a really high one has come along. Let's add, I didn't copy that. Let's add a really high one actually, because then we can demonstrate, I'll put V high, and just for elements of making it more, wow, I'll make it that color. So let's say another one comes along. It's very high. That would get put on the stack. Oh my God, this is a lot of interrupts here. Which is, by the way, this could happen. Anyway, so this one gets finished. It's done. Bang. Okay, so now we're here. And now we're seeing the last in, first out priority ordering. Now this would come out, get executed. This would come out and get executed. And then we go back to our original process, our original program, and we would execute that. Okay, so that is how interrupts work in the A-level level you need to know. And I hope that's been helpful.